Hello, my name is Georgiana Manolake. I am a data science master student at TUE. And this presentation, I will show you my work for the data mining seminar, which aimed at investigating worm starting Bayesian optimization with relative landmarks weighted surrogate models. The agenda includes first a brief introduction into the problem, followed by literature research. Then the problem definition is presented and further explanation of the applied concepts is provided. Finally, experimentation and results are discussed, and then work is concluded with suggestions and future work. A major problem in machine learning, is the choice of learning algorithms. Many algorithms differ in their application, in their approach, for each learning problem they solve, and the data type they consume. Furthermore, algorithms have a number of hyperparameters that often need to be set uniquely for each dataset to improve performance. Thus, the task of picking up the best algorithm and its corresponding configurations becomes rather challenging. While machine learning specialists may use their expertise to come up with reasonable settings, users with little to no background often struggle. Traditional ways of finding good hyperparameter configurations, such as grid search, are very time-consuming and often not feasible given a large volume of data. Several methods that accommodate for such expensive-to-evaluate problems exist. This study considers the method of the algorithm selection problem that use the knowledge of other datasets, typically evaluation scores, to give recommendations for a new dataset. A technique also known as knowledge transfer. Namely, two knowledge transfer methods, the relative landmark and surrogate models, are combined and benchmarked. While there has been continuous research on the hyperparameter tuning problems, recent work relies on the concept of metadata. So now, introduction into the literature will be provided. Meta-learning uses prior learning tasks to learn new tasks more quickly. To do so, it makes use of metadata, which typically comprises algorithm configurations, parameter settings, pipeline components, or network architecture components, and corresponding evaluation measures. While there are several meta-learning techniques which are based on the leveraged metadata, in this study we limit to learning techniques from evaluation measures. Basically, configuration transfer is one strategy which uses past evaluation measures from metadata to predict configurations on a new task. It basically considers two tasks empirically similar if their evaluations are similar. Two configuration transfer techniques are further presented. First, the relative landmarks, which is considering pairwise performance comparisons, usually from accuracy or rank scores, between two configurations on the tasks. The concept has been used as a strategy to either find the best algorithm and ignore the hyperparameters, or approximate the hyperparameters. However, in this study, we will use it as a way to approximate hyperparameters, so the hyperparameter approximation technique. Second, a surrogate model is a model trained using all available metadata in order to produce performance predictions of an algorithm with a specific configuration. So, if a model fitted on a prior task can generate accurate predictions for a new task, then those tasks are essentially similar. Surrogate models, usually Gaussian processes, are used in combination with the Bayesian optimization to determine the next optimal configuration. Early approaches used manually defined meta features, usually for GPs, within the Bayesian optimization. However, this approach is not taken into the study, as meta features defined manually are usually non-adaptive throughout the optimization process. Uetsuba developed a two-stage knowledge transfer, first training Gaussian processes for each prior task and the new task, and then combining those into a weighted sum, to later on be used in the Bayesian optimization. Weights are computed defining a distance metric across tasks. So basically, making use of the relative landmarks, which also do similar measuring. Führer proposed combining Gaussian processes fitted on each prior task and the new task into a single Gaussian process as a weighted combination of the predictions of each prior Gaussian process. Here, the models are weighted based on model ranking laws. Well, in this study, we investigate the relative landmark weighted models effect, which is similar to Uetsuba, but combining weights models into a single model by using both their mean and variance instead of only using the model's means. This is really similar to Führer's, but instead of weighing the models using the ranking laws, we're weighing them on the relative landmarks. This leads us to the research question, which is, does relative landmark outperform the ranking of the models based on the ranking laws in the context of the hyperparameter optimization? Well, to do so, first the Bayesian optimization was further analyzed. So, essentially, Bayesian optimization is a sequential model-based approach to solving problem. It proceeds by iteratively first fitting a surrogate model, typically a Gaussian process, to then use an acquisition function with the just fitted model and the best configuration in the current observed observations to predict the next best configuration. And then this configuration is evaluated on the new task, and the observation history is updated. This proceeds until T optimization runs have been executed and supposedly the best configuration for the new task has been achieved. Several variants of the Bayesian optimization for the hyperparameter problem have been proposed, including procedures in initialization, acquisition function to use, and the type of probabilistic model. For initialization, models from past runs are combined into a single model and then feed to the current optimization run. This is the main focus of the study. Then, for the acquisition function, the expected improvement is chosen, a frequent choice for Bayesian optimization, as it has been shown to give good results for hyperparameter optimization problems. While there are several different model types available for Bayesian optimization, the most popular choice is the Gaussian processes, because they provide good predictions and allow the computation of the posterior Gaussian process as a GP again. What makes Gaussian processes convenient is thus the posterior distribution of samples from a Gaussian prior is still a Gaussian process. Now, where configurations with maximal performance are measured by M, generally a relative landmark is defined as follows. In this study, the relative landmark is defined as a discordant pair of configurations correctly ranked on a task where the F is the sample evaluation function on task T. This approach is similar to Itsuba's work, although the model correctness is not included. So, each model is weighted with the probability that the model is the model with most similar, the model most similar with the model built on the new task for hyperparameter optimization. Thus, the higher the similarity score, the higher the weight. The similarity score is defined as the count of configurations of both tasks which agree. And similarly to the state of art, as samples are drawn from the posterior of each model to be evaluated. And by sampling, overall uncertainty of models is also taken into account when weighting models, which is not done in any other Bayesian optimization. So, for the experiment, we use the metadata generated from a benchmarking function called Alpin1, and you can see the distribution of this function on the left image. And for the procedure, meta-learning